welcome you to another exciting statistical topic. Of course, today we're going to continue from, you know, uh, working on Bayes' theorem and the application. And of course, today we're going to work on application of Bayes' theorem in the court of law. But before we get into that, I'm basically going to share my slide. Okay, those of you online, I believe you can see my lecture slide, right? Can somebody confirm? You can see my lecture slide. Like I said, I may not be able to see charts and I need someone to confirm by talking. If you can see my lecture slide.
Yeah, we can see your slide.
Okay, thank you so much. Okay, so this is the title for today. Of course, we started this yesterday. And of course, I'll call this conditional probability and Bayes rule part 2. Of course, I've updated information in the material that I uploaded earlier in the week. So this is an updated version. Okay, so in the outline, I'll walk you through conditional probability. We're going to talk about independent events. Then from there, we're going to revisit the law of total probability and Bayes rule. Then we also going to look at real life application, and that real life application will come from the court of law. Okay, so I want to walk you through example on conditional probability. For you to be able to understand Bayes theorem on the total probability and the like, you need to first understand what I call conditional probability. Of course, we're talking about conditional probability in the context of two events. Maybe we have event A, we have event B. Okay, we are basically trying to say the occurrence of one event is conditioning on the other one. That's exactly what we mean. Now I'm going to walk you through this example. We use the idea of conditional probability in survey. Of course, where we want to get information from the target population when we're doing our research. We don't study the entire element in the population. We don't investigate everybody. We normally take a sample of elements in the population. So it is that very sample that we're actually going to call them participants, and we're going to ask them question. Take a look at this. A recent survey asks 100 people. Of course, the 100 here is sample size. Okay, if they thought women in armed forces should be permitted to participate in combat, and the result are showed in the table. If you take a look at what we see now, this is this is what we call a contingency table. A contingency table means you are cross tabulating of two variables. The variables are categorical. The first variable here is gender, and that's a categorical. It has two levels, male and female, and the response is also categorical. Okay, it has two levels, yes or no. So this is more or less what statistician is basically going to call analysis of categorical variables. Okay, so you can see the responses. Do you know that we can actually compute a conditional probability, okay, based on what we have now. Take a look at this. If I want to find the probability that they answered yes, given that they were female, I needed to pay attention to a word underlined, given, because if I ask you to compute, how are you going to know that what they ask you to compute is conditional probability? Okay, what are you going to see that will enable you to know that you're actually going to compute conditional probability? You pay attention to conditional word like if, given. Look at that, given. Okay, or they use the word if. Okay, that's a conditional, word. So if you take a look at the word given, of course, and that is how I know I'm being asked to compute conditional probability. When you are working with probability, you need to first like label your events. Now, if you take a look, if you know, say what find the probability the answer yes, I can ask y to denote yes. I'm just using the first letter in a yes. And no, I'm going to use an uppercase N to represent that. Maybe for male, I'm going to use M, and for female, I'm going to use F. But let me tell you, it doesn't matter. If you don't want to use that, you can use the old thing. That's no problem. You will not be penalized for that. Now, when you take a look at the statements, I'll find the probability that they answered yes, given they were female. If you take a look at that, the events of female come first. Okay? And the current event of interest is actually yes. So which is going to be probability of y given f. Does that make sense to everyone? Okay, so now if you look at the formula, the you remember the other time I actually I said, the probability of A given B, okay, is always going to be the probability of the joint, the ratio of the probability of the joint to the probability of B. Take a look at this. This is a formula for conditional probability. Okay. Now, we've been using A and B, but right now we're using a different labels. Doesn't really matter. If you can still make use of this, provided you actually tell me what does A represent, what does B represent. Okay, but for simplicity, I'll prefer you, based on a given problem, maybe you're going to use the first letter. Does that make sense? Okay, so that is so. If I don't want to say, if I don't want to use this, that sign of intersection, I can just use and. They mean the same. Does that make sense? Can just use and. Okay, so if I want to answer the question, okay, what is the probability of? So if you take a look at the ratio, what I have in the ratio, you need to compute two probability. Number one, you need to compute the probability of the joint, which is the probability of being answering yes and being female. And you're also going to find the probability of female. Now, based on what you've done, okay, based on what we've done the other time, okay, based on what you've done the other time, if I want to find the probability, okay, of if I want to find the probability, okay, of y and f, okay, which I also call this, okay, then it's basically going to be equal to the cardinality of this guy, okay, divided by the cardinality of the sample space. Okay, now you're now going to check what is the cardinality here actually represent the number. You understand what I mean? So when you take a look at uh, the table now, yes and female, the yes and female is actually 8. Do you see that? 8. 8 divided by the sample space, the cardinality of the sample space. Of course, that is a total, is talking about the number of participants, okay, that's actually, that's, the interview. So that's going to be 8 over 100. Now, the next one now, you want to find the probability of female, okay? The probability the probability of female is also going to be the cardinality of female divided by the cardinality of the sample space. The cardinality of the sample space remain 100. The number of female, how many female do we have? That's 50, right? Then that was, is there anyone in this class who doesn't understand how I figured that guy out? Is there anyone? Whether in person or online. Okay, now you can go to the next question. Similarly, uh, you're going to find, we're going to go to the next question. Find the probability that they were male, given that they answered no. Okay. So similarly, you're going to go the same way, and you're basically going to obtain your results. Okay. So that is how we find conditional probability. Okay. So I need you to show your work. Okay. Make sure you show your work. Okay. Now we're done with the conditional probability. We want to I want to go into independent events. Of course, yesterday I mentioned that events are independent, okay, if they can occur together. Okay, events are independent, of course, if they can actually occur together. And if they can occur together, don't forget, I said that we attract multiplication rule in probability. Take a look at this guy now. Yesterday, I walk you through two events, okay? When you have two events and they are independent, okay? When two events are independent, okay? Two events are said to be independent if this equal this. Take a look at that. They are independent if the probability of the joint can actually be written as the product of the marginal. This is what we call marginals. This we call them marginals. Okay, when they say marginal, if I say obtain marginal probability, okay, these are marginal. Okay, we also call this unconditional probability. Unconditional probability. Okay, now what if in a situation where I got more than two events? Okay, maybe I got A1, A2, A3, and so on like that. Okay, that is a generalization that you are seeing now. If I have more than two events, okay, if I want to generalize situation where I got A1, A2, A3, and so on like that, okay, like the probability of A1 intercept A2, intercept blah, 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 intercept AN, okay, is basically this multiply by this until I get to the dots. Okay, if I want to write that in the short form, I'm basically going to write that AI, and basically going to put that, okay, of course, I start from 1 to n, but I have to put a condition that my I is not equal to j, okay, where the events are not the same. That's what I mean. Okay, so this is, if I want to write this guy now in a short form, product, okay, this is a sign for product. I start from 1, then I got PAI. So this is representing this guy. Does that make sense? So this what I just show you now is when I have more than two events, and that's exactly what I'm displaying on the board. Okay. Now we can say if an A1, A2, A3, A4 are mutually independent, if all of that hold. Let me tell you, if you want to, if I can give you some say, like for instance, you have A1 up to A4, and I ask you to prove whether they are mutually independent. What do I mean by mutually independent? The mutually independent, you need to foresee whether when you look at that in pairs, are they independent? When you look at them in threes, are they independent? And when you look at all of them together, like A1, A2, A3, A4 together, are they also independent? Then because of that, when you verify all of that, then you can say they are mutually independent. Let me tell you this: if you have A1, A2, A3, A4, if A1 and A2 are independent, and A3 and A4 are independent, but A1, A2, A3 are not, then they are all of them are not mutually independent. Please take notes. Okay, that is why actually display that. Now from there, I'm actually going to move to continuity theorem. When I'm talking about continuity theorem, we at times we could have some sets that actually that can be contained in some other sets. The same way a particular school in this university actually contained in the university. So which means the university is bigger in terms of size. Now take a look at what we see here. Let A1, A2 be an increasing sequence of events. When I say increasing sequence of event, it means the number of elements you have in A2 is more than the A1, A3, more than like that. That's increasing. Does that make sense to you now? So because of that, I'm going to say A1 belongs to A2, A2 belongs to that, and so on like that. That's what that notation means. And you know what? If I can I can talk about the limits as n tend to infinity. So the probability of the limit of the sequence is basically going to be the same thing as the limit of the probability. Okay, that is exactly what we mean. And in that situation, where A1 is belonging to A2 and so on like that, we can also have situation where the limit ascending to infinity of AN is just going to be the union of all the events. Okay, that is just what the continuity theorem is talking about. Okay, I want to go into something more interesting, which I call the law of probability and the Bayes rule. I'm actually going to revisit this, and we're actually going to apply this to a celebrated case, the case that I'm actually going to call the trial of the century in the United States in 1990, I think 1996, the O.J. Simpson case. I don't know whether anybody has heard about O.J. Simpson case in 1996. Okay, I'm actually going to give you the description. We're actually going to use the Bayes rule. Okay, so before we can apply this Bayes rule now, I first want to walk you through the Bayes rule. Of course, yesterday I derived the Bayes rule. Okay, so take a look at this. This is the specification of Bayes rule when the sample space is partitioned into two. What I'm going to do is this. I'll first walk you through the application of Bayes rule in medical diagnosis before we go into the court's application. So I need everyone to pay attention. Focus on the board. Those of you online, when you chat with me now, I may not be able to see what the message. But the only way I can respond to you is when you talk. Okay, I mean those of you that are online. If you chat with me, I may not see that. Okay, I need you to talk in case. But before I continue, those of you online, can somebody confirm by talking if you see or hearing me clearly? Those of you online.
Yeah.
Okay, thank you so much. Thank you for confirming that. Okay, so if you take a look at special case M equal to 2, we can have a situation where the entire sample space can be partitioned into more than 2. I showed you yesterday. But here I only want to focus on just partitioning into two categories. Now, when you are partitioning the sample space into categories, you're basically going to use complements. Okay, where one is going to, like here now, B and B complement. Does that make sense? Okay, so take a look at that. B and B bar. So the bar, the one with the B bar now is actually the complement of B. Okay, it's either you belong to B or you don't belong to B. It's just like right now, it's either you are in my class now or you are not in this class. That is what I mean. Okay, does that make sense? Okay, now the Bayes theorem, the probability of B given A will actually be equal. Of course, yesterday I show you that if I have the probability of A intersection B is the same as the probability of that. Okay, commutativity, right? Okay. Now, when you take a look at this guy, when I start with this guy, okay, multiply by this guy. If I start with this guy, then I'm actually going to have that. Does that make sense? Okay. Does that make sense? This is a situation where A and B, they are not independent. They are not independent. Okay, not independent actually imply they depend. That's what it means. Okay, now if I want to find the probability of B, if I want to find this guy, I'm actually going to solve, right? I'm going to solve for that guy. So which means I'm basically going to have this guy equal the whole of this guy, the whole of this guy, okay, divided by the probability of A. Okay, now let me tell you this. Somebody asked an intelligent question yesterday. That's why do I call this one the total probability? Of course, when you have a probability, if this guy is a probability, the denominator of a probability should be sample space. It should be total. Does that make sense? So if I want to rewrite this guy now, and this guy, inside this guy, you have this guy too. Don't forget, when I'm talking about probability of an event, okay, it's just going to be that event divided by the sample space. The sample space also include the event. Does that make sense? So when you take a look at this now, if I want to rewrite this guy, okay, I want to rewrite the probability of A. And this guy is going to be part of the probability of A. I'm going to write this guy now. Okay, then the remaining one is still going to be focused on A, except that it's not going to be B anymore. That very B will be B complement. Take a look at that now. I'm actually going to have this guy now. Look at that. That's a total probability. That's exactly what you are saying now. Does that make sense? Okay, now that is why this guy is called a total probability. Now let us now apply it in medicine now. Okay, let me tell you this. We live in a world where there's a variation, and the moment there's a variation, there could be possibility of mistake. Okay, this is not a perfect, when you use a model to capture reality, our model cannot give us exact reality. There's always going to be an error. Okay, so I want to tell you this: in medical diagnosis, the equipment used in medical diagnosis is not 100% efficient. Does that make sense? Now, the idea of the Bayes theorem can actually be used in a medical diagnosis. Now, let's take a look at this. In screening for a certain disease, okay, the probability that a healthy person wrongly get a positive result is 0.05. Somebody is healthy, he doesn't have the disease, but the machine can say so, and that occur, the probability is 0.05, which is very, very small, right? Okay. Okay. But that is not zero. If that is zero, that is basically going to suggest the equipment is perfect, right? Okay. The fact that you have a number, it means the equipment is not perfect. Now, the probability that a diseased person wrongly gets a negative result, okay, is 0.002. Okay, that is not also perfect. Now, the overall rate of the disease in the population being screened is 1%. If I go for a test now, if my test give a positive result, what is the probability that I actually have the disease? Okay, the Bayes theorem is going to come in. I need you to pay attention to how I'm actually going to solve this using the Bayes theorem. And after doing this, then we're going to go to the court of law. Because in the court of law, okay, if the medical equipment is not perfect, then the judge is not also perfect. Okay, and that's why I don't pray to have a case. There's nobody that is sure winning a case, even if you have evidence, strong evidence. Okay, so if you want to, if what you need to do first, okay, what you need to do first, the sample space now is partitioned into two. Okay. It said if my test gave positive result. Okay. When I say positive result, okay, I'm going to say let this represent positive result. Okay. A, event of positive result. B, A bar, okay, negative result. Okay. How is the sample space partitioned? Oh, those who have the disease and those who do not have. Does that make sense? So I'm basically, uh, if you take a look at B and B bar, okay. Now it said if my test is not, what is the probability that I actually have the disease? So I'm going to say B, okay, event of B, disease is present. Okay, because I want to use that formula. Okay, what about B? Okay, disease is absent. Who doesn't understand how I interpret that? Doesn't understand that? Okay, do you know what we want to find? We want to find the probability of B given A. Let's see, B given A. That is, B given A, I have a positive result. Okay, what is the probability that its disease is present? Can you see that now? So which means what I want to find is the probability of B given A. That's what I want to find. That's what you have. Look at that. B given A. Okay. Now, the next thing you're going to do now is what is the probability A given B? Okay. A given B. Now, what is A and B? Positive result, disease, right? Positive result, disease. Okay. If you take a look at what we have, okay, so this is going to be the probability of A given B, okay, multiplied by the probability, okay, of B divided by the probability of A given B, the probability of B plus the probability of A given B complement the probability of B complement. What you basically need to do is this. Now, this guy, you want to find it? Okay, disease is present, right? Positive result. Okay, now if I have, but what you are given in the question say, the probability that a diseased person, okay, what do I use to represent diseased person here? Disease person, B, right? Okay, diseased person, okay, wrongfully get a negative result. Deceased person wrongfully get a negative result. I need someone to tell me out of what I have on the board, which one is going to represent, which one is going to represent is 0.002, and which one is going to represent is 0.05 for extra credits. Can someone tell me? Extra credit? Based on, I'm going to fill up this one now. Disease is present 1%, right? 1% of the time. 1% is 0.01, 0.01. And of course, this guy is going to be easy, right? 1 minus this, right? What is 1 minus 0.01? Is it 0.99? Okay, 0.99. Okay, and this is, we have already obtained this guy. The only one that we haven't obtained now is this guy and this guy. Okay, go ahead. Which one represent is 0.002? Oh, you wanted to give this guy? Okay, probability of A giving what? Giving B bar. Now let us see. Now is 0.05. It said any person wrongly gets positive result. Now, what do we use for positive result? A, right? Okay. Now, if any person gets negative result, let's see, that's a bar, right? Do you see that? Can you see that, right? So, which means you are talking about this guy. Okay. Positive result is this, but B bar is, what is B bar? Oh, no, that is not one. That's not the one. Disease person. The disease person is supposed to be disease is present. Yeah, of course, B. Do you see that now? Yeah. For 0.05. Which 0.05 represent which one? Here. What does it represent? Yeah, that's what I'm saying. Like, which one do you think? Because disease is present has to be B. Okay. Okay. So if you say you're trying to say the probability of A given B bar, right? Okay. Let's see. Disease person. Disease is present. Is deceased person. Okay. Any person, disease is absent. Okay, yeah. Then, yeah, yeah. That makes sense. I think I also saw you raising up your hand. So which one do you want to help us with? Or you were saying about, is that what you wanted to choose as well for what is 0.05 represent? That's what you want to choose, right? Okay, now when you take a look at this, if this guy is 0.05, which means the edit person is actually B bar, which is disease is absent, right? And A, an edit person getting a positive result. You know, that's an error, right? Okay, so the conditional probability in the A, we're actually going to come in terms of the error. Does that make sense? So if I write this one as a 0.05 now, okay, now if I want to get this guy, okay, if you take a look at what I have, A giving this one now, okay, now I want to get this guy, but before I can get this guy, let's look at the 0.02. The probability of a deceased person, okay, wrongly, okay, the probability of a deceased person wrongly gets a negative result. Now, deceased person now is B, okay, getting a negative result. That is a BA bar. Does that make sense now? So if I have BA bar, so what is trying to tell me is A bar giving B, you know it, based on what we did yesterday. Can somebody tell me? I think I asked you to prove something that what I have here, there's going to be a complement, right? and this is going to be the same. Does that make sense? Look at that. Do you remember what we did yesterday? This one here is what they actually gave you as is 0.002, but that is not what we need in our formula. We don't need that, but we need this to be able to compute this. This is the one that is here and here. So so this is going to be 1 minus 0.02 now, 02 now, and 1 minus 0.02. Does that make sense? So please take note. So whatever you get is going to be your result. Now I actually want to move. Now let me tell you the idea behind the Bayes theorem. In Bayes theorem, this guy here is going to be called posterior. Posterior. Okay, posterior. So this is going to be called, okay, that's what I want you see me displaying. And this guy will be likelihood. And this is going to be prior. Okay, the prior actually means our belief before we collect data. I told you the other time, our mind can never be empty. Okay, our belief before we collect data. And after collecting data, data is going to come in terms of evidence. Okay, now I'm now going to update with the with the evidence available in form of data. We're actually going to update our belief. Okay, updating our prior belief is what we call posterior. So which means as given by Reverend Thomas Bayes 1759, okay, is trying to combine the prior knowledge with the likelihood to get the posterior. So which means we're basically going to have, so that's what you see me displaying. When you see probability of A1, A2, what those are prior probability. They're also called marginal probability. They are also called unconditional probability. Why the other one is going to be likelihood, and combining them, you basically. Okay, so I'm going to go to another example on car warranties. Okay, a company says a certain type of car, which it assembled in one of four possible locations. Plant I supply that, plant 2 supply that, and so on like that. And you also have, each new car sold carries a 1-year bumper to bumper warranty. And you were given all of that in terms of a conditional probability. So those ones are your likelihood. Now the question now, claims are clearly not independent of assembly of location because these 4 probabilities are unequal. Now you can make use of, you want to find the probability of a claim. Let me tell you, the probability of a claim is a total probability. I'm going to say that again. The sample space here is partitioned into 4. How many factories? Into 4 locations. It's to 4 plants. Plant 1, plant 2, plant 3, plant 4. Does that make sense? So the probability of a claim could come from factory this, factory this. So that is why the probability of a claim is basically going to be a total probability. So the probability of a claim is going to be, a claim could come from plant 1 or plant 2 or 3 or 4. Okay, that is why you have all of that. So using the tree diagram, basically going to be easy for you to. You want to ask a question? Go ahead. Why what? Oh, that is given. All these are given. We're always going to collect data. We're always going to have data. The company know the volume of claim they receive. You understand what I mean? So all these are already given. Okay, so they are already given. Okay, so you actually get that. Now after getting this, you can now find a posterior where they're basically going to say if a claim has been made, what is the probability that is from plant 1? That's posterior. You see now, what is the probability that is from plant 2, given that a claim has been made? Okay, so the probability of the claim is the total probability that you need to first figure out. Okay, this is the way we got the total probability. The probability of B now, B is representing a claim is made, which is going to be the combination of the prior. Okay, it's going to be the combination of the prior and then look at the conditional, the probability of A1 times probability of B given A1. The A1, A2, A3, A4 actually represent the factory. Does that make sense? Okay, so that is what you get here. When a claim is made now, you can see that you've computed the probability, that is basically going to come from plant one, two, and so on like that. Then when no claim is made, if no claim is made, of course, your total probability will be no claim. Does that make sense? So which means you actually need, you can say in the denominator, what do you see? The probability of no claim. Of course, if you know the probability of claim, the probability of no claim will be the complement of claim. Does that make sense? Then you're also going to get all of that. Now, I want us to use the remaining time. I think we have like um, 10 more minutes, to talk about the court case involving Simpson. O.J. Simpson was American professional football legend. Okay, and he also, when he retired, I think he worked with NBC as sports analyst. And something happened in the state, in Los Angeles in 1994, June 12, 1994. The ex-wife of Simpson, the was actually murdered. Okay, not only the ex-wife of Simpson, also Simpson's friend, because based on the story, it's like Simpson, the ex-wife of Simpson, were actually going, having a relationship with Simpson's friend. Okay, but they found the LAPD found the body of the ex-wife and the friend, and what the evidence they found on the crime scene, match the one that was found in Simpson's car and Simpson gloves. Okay, so the blood stain, okay, actually matches, and that's why we advise that you don't go near a crime scene. Okay, you don't go near a crime scene. Okay, now the Simpson was actually alleged of responsible for the murder. Let me go into that one. Give me 1 second. Is this one I'm talking about? Uh, Nico Brown was the ex-wife of Simpson, and of course, like I said, um, another evidence before. I think the relationship between Simpson and his ex-wife was not that rosy, because I think Simpson has uh, history of domestic abuse, and that was also, actually uh, very useful in the trial. But let me tell you this: despite the evidences available, because my time is not going to allow me, but when I what I'm going to start from, where I'm going to start from tomorrow, I'm actually going to start from showing you how the Bayes theorem was used in this case. But eventually, Simpson was discharged and acquitted despite overwhelming evidence. But let me tell you, the argument was this: because in the court of law, they asked Simpson to wear the glove, and that very glove was not fit. You understand what I mean? Even though some law students have really argued that out, that something you, if you did not practice something in advance, don't do it in the court of law. Okay, so the analysis of the gloves is one of the reason why Simpson, won the case. Another reason, the defense counsel of Simpson, they use what I call frequencies approach, because the guy claimed that it is only 0.1% of husband who actually abuse their wife, eventually murder them. So he realized that that probability was very, very small. But the defense counsel did not realize the fact that somebody was murdered. So, which means it was actually using frequencies approach. It did not put into consideration the base, because the base is basically, uh, oh, sorry, give me 1 second. The base is basically going to consider all of that, which I'm going to show you in the next class. But do you know another thing that make Simpson to win the case? The defense counsel actually changed, they diverted that case from, whether Simpson murder to the performance, the behavior of LAPD to a particular race in Los Angeles. Because as at that time, the the LAPD did not have a good relationship with a particular race in Los Angeles. And if you look at the jury, the jurors that selected, of course, majority of them belong to that race that I'm not going to mention. And that's within 30 minutes. That this particular case that I talk about, you know, was the case of the century because it was a case that was televised as at that time in the United States. But why am I bringing this on? I'm bringing this on because of the fact that we live in a stochastic world. The fact that you have a genuine evidence when you go into a court, if your attorney assure you that you have 100% of winning, change your attorney. There's nobody who have 100% of winning, even if you have an overwhelming evidence. You know why? Because the judge is not perfect. And another thing is, no, none of the side involved in litigation, okay, is completely innocent. And that's why I don't pray at all to be involved in litigation. I don't pray at all. So make sure you try as much as possible to avoid confrontation, avoid anything that will take you to the court of law. You get what I mean? But you know what I'm going to show you next time? I'm actually going to show you how. Let me tell you, we use Bayes' theorem. The probability that Simpson murder his wife is actually high, but there was another probability that was higher than that. The probability that, based on the evidence, the probability that the LAPD frame Simpson was higher than the probability that Simpson murder his wife. Okay, so like I said, there's a lot of things they put into consideration in judging a case. I want to believe there's so many factors. They have aggravating. There's something they call aggravating factor. There's a lot of factors, and that's why I don't tell pray at all to be involved in litigation. But I'm going to show you. They still argue that today that that very case should not have gone the way it has gone. People believe it's a mistake by Simpson. I mean, by the prosecutor, the prosecution lawyer, because the prosecution lawyer was the one that asked the Simpson to wear the glove in the court, and that very glove did not size him. And they said they charge him and accused it. But the fact that that did not size, there's a lot of things that could happen, you know. So I'll demonstrate that to you using Bayes' theorem tomorrow. Now, this way I'm actually going to stop today. Is there any question before I go today? Any question? Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.